I'm going to go into this discussion of some basic sorting algorithms with the belief that you've already studied bubble sort. You have a good working knowledge of it. If that's not true, then you probably want to go look at bubble sort somewhere. Um, so if you understand bubble sort, you realize that to sort an array, you have to take multiple passes through the array, and that at the end of the first pass, assuming that you're trying to sort the array in increasing order, at the end of the first pass, the largest entry will be at the end of the array. And then on the second pass, the next largest entry will be right next to it towards the end. The first pass through an array of length n requires doing n minus 1 comparisons. The second pass requires n minus 2 comparisons. The third pass would require n minus 3. And I'm speaking in general, and I'm assuming we're using a version of bubble sort that doesn't detect that it can end early. So with this basic bubble sort in mind, we can figure out exactly how many comparisons have to be made, and we'll do that in a few minutes. So along with bubble sort, there were two other very standard, if I might say, somewhat simple-minded sorting algorithms, and you very likely encountered at least one or both of these by names of selection sort and insertion sort. Selection sort does perhaps the most obvious thing. It simply goes through an array, and in a single pass it finds either the largest or smallest entry in that, and remembers the location where that occurs, and then it swaps that entry into position at one of the ends of the array. So if it looks for the smallest entry and you're trying to sort in increasing order, it'll swap that smallest entry to the beginning of the array, whereas if it looks for the biggest entry, it'll swap that to the end. And of course, it's reasonable in one pass to do both of those things at the same time, but that's complicating things, and we don't need to worry about that slight variation. I guess of the three basic sorting algorithms, insertion sort is slightly more complicated and actually has certain advantages. It uses a slightly more, less obvious perhaps, strategy, as we'll see. It too takes multiple passes through an array, and as it goes along, it makes an effort to keep the initial portion of the array sorted. So by the end of the first pass, we can say that the first two entries in the array are in the correct order relative to each other. Okay? And then on the second pass, we can say that the first three entries in the array are in the correct position relative to each other. Not that they're positioned where they're ultimately going to end up at the end of the algorithm, but merely that initial portion is sorted as we go along. Okay, well, here I'm talking about bubble sort, but it actually turns out that if you analyze, and we will take a look at code for these algorithms, you think about the fact that each one is a loop within a loop. Well, let's talk specifically about bubble sort. As I said, the first pass requires n minus 1 comparisons, and each of those might or might not lead to a swapping of two elements. But let's simply say that on the first pass, n minus 1 comparisons are made, and that basically we can bound the time that it takes to make that first pass as a constant amount of time multiplied by n minus 1, because n minus 1 is the number of comparisons. Okay? The second pass, it would be bounded by a constant times n minus 2, and so forth. When we get down to the last few passes, we have a constant times 3, a constant times 2, and a constant times 1. Okay, if we ignore that constant factor, then we're just adding the numbers n minus 1 plus n minus 2 plus n minus 3 plus dot 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 to plus 3 plus 2 plus 1. And of course, I've written here the same thing, written in reverse, though. 1 plus 2 plus 3 plus dot dot dot, and it ends with n minus 1. Okay? Well, it's a well-known fact, and it should be known to you from basic course in discrete math or some such thing. If you add up the numbers from 1 up to n minus 1, there's a very well-known formula that says, well, that's going to be n times n minus 1 divided by 2. Okay? And then if you look at that carefully, that's the same, that's 1/2 n squared minus 1/2 n. And of course the dominant term there is the 1/2 n squared. So we're saying that n times n minus 1 over 2 is dominated by 1/2 n squared, and that of course is capital theta n squared. Okay, I was about to say a moment ago that we'd get basically the same analysis as the other two algorithms, but that was a slight misspeak. We get the same basic formula for selection sort for essentially the same reason, that 1 plus 2 plus 3 plus dot 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 business. With insertion sort, we have to be a little bit careful, as we'll see. Okay, anyway, here's some source code for these algorithms. For a couple of the algorithms that we're going to study, it'll be handy to have a little swapping function just to simplify things for us. And I should, of course, say that the code I'm going to present is C code. And if C code, or if you have not studied C or C++, enough of this might look familiar from Java that you'll get the basic idea and not have to worry about the finer points. For example, this word inline, which is part of C and therefore C++, is not used in Java. And you could, well, I'll just mention that it is concerned with speeding up the code in some way. Okay. The ampersands on double here mean that we're passing data to the swap function by reference. And what that means is that we're not really passing the values, we're not passing by value, but we're really passing the addresses of some data. And so if you go on and you look at the body of this function, you quickly see that all it does is swap what's in x and y. It uses a third variable z to pull off a swapping. The usual thing, x gets copied into z, a local variable, and then y gets copied into x, and then z gets copied into y. So the upshot is x and y get swapped. And of course, it's the actual data that's passed as arguments. It's the actual arguments that are passed when the swap function is used, as we'll see it used in a moment. It's the data there that's actually swapped. Okay, that was somewhat tedious, but with all of that as backdrop, we're going to look now at code for the three algorithms, and in all three cases, I think you'll be looking at some pretty cryptic code, very short and sweet, and hopefully, in fact, it's rather important that you take the time to step through it carefully until you're convinced that it does what it's supposed to do. Okay? So in the case of bubble sort, I'm passing to this function bubble sort an array of doubles, which I happen to name P. P is not a very suggestive name for an array, but there it is. Because C and C++ are incapable of figuring out the length of an array, unlike, say, Java, I am also going to pass as a second parameter here, I'm going to have capital N, which is going to receive the length of the array when bubble sort is used. Okay? And then it's just simply a matter of nesting two loops. Hopefully you're not disturbed by the absence of curly brackets here, but following C syntax, I have an outer loop whose body is an inner loop, and the body of that inner loop is simply an if statement. Okay? So you can see from the outer loop's header that there's a counter involved, and that counter I, that counter variable I, is going to decrement from n down to 1, and when it hits 1, it'll quit the outer loop. Okay. Then the inner loop is going to be controlled by a counter variable j, and this time j is going to increase. It's increment each time, so j will go from 1 up to I, and when it reaches I, it'll quit the inner loop. Okay? And then the body is simply what you'd expect from bubble sort. There's a comparison of two adjacent entries in the array, p bracket j minus 1 and p bracket j, and if they're not in the right order, they get swapped. So that's pretty simple. So the trick here is basically to check to make sure that you believe that the outer loop and the inner loop are exactly right, and I'll leave that to you.